In quantum optics, a single-mode field is specified by a quasi-probability distribution in position and momentum. We show here the example of the Wigner distribution for a coherent state. The intrinsic uncertainty of the state is depicted as a circle, which is simply an isocontour line of the Wigner function. In a Kerr medium, the light experiences an intensity-dependent phase shift during its propagation. In the single-mode case, this leads to a self-phase modulation. For an initial coherent state, this results in an elliptical noise distribution, that is, a squeezed state. In the cross-Kerr configuration, the refractive index of a beam is modified by the intensity of a second one. These beams are excited in two orthogonal polarization modes, so this is better described in terms of the Stokes parameters. In classical optics, any state of polarization can be uniquely represented by a point on a unit sphere, centered on a rectangular Euclidean coordinate system, the Poincaré sphere. In quantum optics, fluctuations in the number of photons are unavoidable, so we are forced to talk of a three-dimensional Poincaré space which can be envisioned as foliated in a set of nested spheres with radii proportional to the corresponding photon numbers. The state is not located in a single sphere, but distributed over different shells, like in an onion. Our states can also be represented by a Wigner distribution in Poincaré space. Again, as a typical example, we show a coherent state which has equal uncertainties in all Stokes observables. The isocontour surface of the Wigner function in the Poincaré space gives complete information about the fluctuations of the state. We show here the time evolution of such an isocontour. As it can be appreciated, the state gets elongated along the direction of maximal squeezing.